We are Pneumatic WORX, and I am Mark Weirnuz.
I'm Jeshurun Sestito.
I'm Yenca.
I'm Anastasio.
And I'm Jeshurun.
And our advisor is Dr. Zhu. Some of the items that we will be covering today include what is Pneumatic WORX, the roles of each individual, the introduction to our system, the current solution, our solution, including the requirements, the specifications, and each single item. Why we use pneumatic actuators, the animation of our system, why we use the EMG sensors, the cost analysis, work schedule, calculations, testing, and the references. Right. Some of you might be wondering what the WORX in Pneumatic WORX stands for, and that is Wearable Orthotic Rehabilitation eXoskeleton. And if you look to the right, you will see a 3D model of our system.
So I will be taking care of the programming and doing some work with the computer-aided design.
I'm going to be in charge of material selection and project management.
I'm in charge of computer-aided design.
And I'm going to be in charge of the calculations, fabrication, and final assembly.
I'm also doing calculations, fabrication, and final assembly.
So for a little bit of background on the problem that we're actually solving with our design, current injuries are associated with sports injuries such as like ACL injuries and MCL injuries. ACL is actually an acronym for anterior cruciate ligament. It is what is the primary ligament that is associated with injuries from overextension or like sudden bracing and stopping. So in football or baseball, when you go to suddenly stop, that's usually what gets torn if you actually tear a ligament. The medial collateral ligament, that's what MCL stands for, that ligament is usually torn in a very quick, rapid torsional motion on the knee joint during an activity such as that. So it's very common among athletes and others alike. It's a very painful injury and it can leave you immobilized for several weeks with current solutions that are out there. Approximately 100,000 to 200,000 ACL injuries occur annually in the US. And so that shows that our problem is very current and really needs a good solution. Active orthotic devices such as ours would be able to reduce the recovery time of such injuries by allowing movement within the knee joint, which actually aids in recovery of the system, allowing blood flow to the area that has been affected. The current solutions lock your knee in a stable position, allowing for limited range of motion and mobility during the recovery process. So we aim to actually increase the mobility and allow for the user to fully walk in a normal gait while they're recovering. The kind of solution that they have in this picture is actually one of the current braces out there. And as you may notice, there is a degree locking system on the knee joint, which prevents you from overextending your leg or underextending it during recovery. The recovery from ACL surgery can actually take up to 9 months. So one of our goals is to reduce that time using our system.
The requirements for our solution are it must reduce the recovery time for the user. It must provide a range of motion from 0 to 71 degrees. It must allow or take the load off of the knee joint and the tendons. And it also must be safe and comfortable for the user. Safety is a really big aim for us, so we will be including an emergency stop system, a pressure relief valve, and also a mechanical stop system that is included in our knee joint, which will be discussed later on.
And as for our specifications, we aim to use pneumatic actuators to give us the force necessary to rotate the leg of a fully grown adult human to the motion mentioned before. We will also use EMG sensors in our design, but they will be further explored later by Jesh. We will also use compressed air tanks in place of other systems such as like a air compressor and a battery combination. This will help reduce weight and cost, and it will also make the design more user-friendly. And we will use a pneumatic solenoid valve to divert the pressure from the air tank into the different muscles based on the output from our Arduino microcontroller. And we will use adjustable straps in our design to accommodate a larger range of possible customers. And we will use a aluminum frame. This will help us cut more weight and also not impede our structural integrity. And then why use pneumatic actuators? We are going to use pneumatic actuators because they're relatively inexpensive and easy to produce in-house. So this helps save a lot on the cost aspect of it. And the muscles have the ability to use the torque necessary to actually move the leg of a fully grown human man. They will also help make the system feel more natural as the muscles act as a natural muscle would through expansion and contraction. And this also allows for a portable air supply. So again, we don't have to deal with a bulky and cumbersome system.
So for our passive ankle joint, our solution is shown below. For those of you who've seen it before, we have indicated by the arrow our old system. It was very large and bulky, so we did have to do a redesign, and we actually made a simpler, more compact structure, which is shown in the other three images. This helps relieve pressure on the ankle for the user, and it also helps stabilize our overall system.
For the frame, we decided to use 6061 aluminum rectangular tubing. This decision was made because we wanted the frame to survive daily use while bracing the knee, yet still be lightweight enough to not impede any movement or add any extra strain to the body. And shown here is our current 3D render in SolidWorks of our design. The most pivotal, no pun intended, point of our design is the knee joint, which can be relocated by the circular metal discs. This joint will rotate about a central axis when actuated on pneumatic muscles, and will rotate in a similar fashion as a knee. The design is also focused towards comfort, and it can be noted that there is glue padding on the frame itself and the foot to provide an overall more comfortable design, similar to those already in use. The straps, as mentioned before, will also be adjustable for different leg sizes, and we hope to add position placement as well for different leg lengths. In the future, we hope to add a frame around the pneumatic muscles themselves to hide away the mechanical system to give the design an overall more sleek look. And we also plan to add a belt attachment so that it connects directly to the belt which houses our air tank. We also plan to add more padding around the knee. Despite our design won't actually touch the knee itself, we want to be safe just in case if your leg moves or anything like that. We want to make sure that it's all nice and comfortable and will be fully functional. And here's a small animation that we worked on. In the future, we want to make it more clean and concise, but you can see the muscles actuating slightly as the knee joint rotates.
So you may be wondering what EMG sensors actually are. So EMG is actually an acronym that stands for electromyography. And the definition of electromyography in our use for this system is the recording of an electrical activity of muscle tissue, and then using that electrical signal to actually graph and plot the output from those sensors. That can then be used to control our pneumatic muscles, to sync it up with the actual walking gait of a person, so that while they're walking and while their muscles are actually contracting, we get an electrical signal, and then can tell our actuators to actually actuate and assist them. So in this video, as the subject opens and closes their hand, the electrical signal is sensed by the electrodes on the forearm, and then the graphical display is put on the computer. The board seen in the video is a Bitolino, and it's actually a multi-purpose biological sensor. So there are other ports on that as well, and it actually has an accelerometer, so if we wanted to do position plotting and actually graph the position of the leg while walking, we could. That program that is on the computer in the background that plots it is OpenSignals, and that is a direct download from the Bitolino website in order to actually process the data. And they communicate via a Bluetooth chip, which is this green chip that you can see right there on the Bitolino.
All right, so next we're going to talk about the cost of our system. We're sourcing our parts from 4 different places. The first one being Amazon, the second being Anastasio, which is a paintball supply company, the third being Bimbo, which is a hydraulic and pneumatic supply company, and the final source being McMasterCard, which is an industry leader in hardware supply. So going over our Amazon list, most of the things on here are directly related to the construction of our muscles, so tubing, fittings, and things of that nature. We also have our Arduino Uno listed here. We already have sourced an Arduino Uno, but it was included in the cost analysis as if we were starting from scratch. As for the ANS gear source, we are going to be getting 2 parts from there. We are going to be sourcing our compressed air tank, Next, we have the bimba source. The only thing we are sourcing from here is our solenoid valves. Once again, these solenoid valves will be controlled by the Arduino to allow air to pass in and out of the muscles. Finally, we have the McMaster-Carr source. We're going to be sourcing our rectangular aluminum tubing and our flat plate for the foot of our apparatus. Hopefully we can source most of this material from the machine shop, but it is included in the analysis once again as if we were starting from scratch. Next, we're going to go over the schedule for our design. So our sinusoidal testing, first round was finished earlier this week, so that puts us right on schedule. We are hoping to have our prototyping start the beginning of January and finish that by the end of February, beginning of March to allow ample time for optimization. Next, we're going to talk about the torque necessary to actuate our device. So some information we use for this is the subject is 500 pounds, 6'5" to allow a 6'6" to allow a ample high safety factor. So to find the torque necessary, one must first find the moment of inertia of the leg of the patient. Once this is done, then we did further research on the angular acceleration of the knee joint while walking. We found that the maximum angular acceleration is roughly 40 radians per second squared. So using these two pieces of information, it can be found that the torque necessary to move our leg is roughly 18 newton meters or 13.13 pound-feet of torque.
And as for testing, we just utilized a workbench from a previous senior project that Mitch had, and we basically just attached a lever arm with a screw to the one 4x4 beam, and then we attached the pneumatic muscle in between the two vertical beams in a vertical fashion. And we attached a hanging mass of 1.3 feet from the pneumatic muscle, and this is what we came up with. And also the supply pressure for this test was not known, as we used a air supply just in lab without any sort of regulator or pressure sensor of any sort. So we don't actually know how much pressure was going into the muscle, but this serves as more of a proof of concept that we can build and actually actuate the pneumatic muscles.
Here are our references. Any questions?
Just from the motion seems to be very jerky motion. It's not really smooth.
Mm-hmm.
You know what I mean?
Yeah, we would have to do pulse width modulation on the actual solenoid valve to allow air in bursts to get that kind of more linear, smooth contraction of the muscle. Yeah. Back.
Go back to your overall design.
The first slide or this one?
Yeah, I'm just curious why you're going with a full length system instead of just isolating the knee joint separately, and why you're incorporating the ankle.
We're incorporating the ankle to provide stability to our system, and that way that's a control point that we can actually measure and keep at a certain angle while in the walking process, so that you're not, because we're using an actuator, we don't want any issues with like somebody injuring their foot while using this, so that's actually a safety measure to make sure that we can control where their foot is while placing it in a stepping motion. Yeah.
You got your next slide?
Next slide.
Next one. This one.
Yeah.
So when you put that video, it looked like you got a clear signal, but it was rather noisy.
Mm-hmm.
What considerations have you made for signal processing so far?
We're thinking about like Fourier series transforms in order to actually plot it and get the peaks, and then modulate those peaks in series with the actual actuation of the muscles during walking.
Okay.
Yeah.
I just wondering just one thing. The healing process for MCL versus ACL injuries is a little bit different. You need different stability from the knee. So just when you're I would probably pick one or the other to program it towards, just because the healing process for them is different, because one is a forward back movement, one is side to side movement. So you just want to make sure that the knee is stable in the whole process in terms of which injury it is.
Right. Thank you. Yeah.
You guys reached out to, the athletic training department here at WORX at all?
We have not yet. That's actually something we're hoping to do in the future for our design, to get some input from them as well on the recovery process for both injuries, and then what would be the best way to stabilize that and padding for it as well. Anyone else? Thank you.